Hi, my name is Sarah Harris, and I'm a professor at the University of Nevada, Las Vegas. And today I'm going to talk about the textbook that David Harris, my colleague at Harvey Med College, and I have just written. It's called Digital Design and Computer Architecture, RISC-V edition. So we've adapted our popular digital design and computer architecture textbook to cover the RISC-V architecture. And so two of our prior books are Digital Design and Computer Architecture Second Edition, which was published in 2012 and covers the MIPS architecture, and Digital Design and Computer Architecture ARM Edition, which was published in 2015, but obviously covers the ARM edition. So the expected publication of the RISC-V edition is August 15th of this year, of 2021. So to give some statistics on our prior books, they're used internationally, and in the US, in the last year, for example, it was used by 10,000 students, university students, and the books have been translated into 6 languages, so available in 7 languages: English, Chinese, Japanese, Korean, Spanish, Russian, and Portuguese. So the material may be taught, it clearly has these two sides, digital design and computer architecture, and it can be taught as a single course or as a 2-course sequence. And so, for example, at Harvey Med College, we teach it as a 1-semester course, and at the University of Nevada, Las Vegas, we teach it as a 2-semester course, first digital design, and then the second semester, computer architecture. We've also developed a MOOC available on edX. You can search via digital design Harvey MedX or computer architecture Harvey MedX. And so this MOOC is divided into the 2 parts of the book as well. So one question, why RISC-V architecture? Why we've written books on MIPS and ARM and now RISC-V? Well, some advantages of RISC-V are that it's open source. And so the barriers into being able to use the architecture are, a lot less time and cost. Also, RISC-V has base instruction set architectures, base ISAs, RV32, 64, and 128. And this base instruction set makes it so that you can run the compiler and optionally include extensions. And so that's the third point. It's extensible, so you want to include floating point, you can using an extension, but you're not stuck with implementing instructions that you don't need for your implementation. Also, RISC-V is increasingly adopted commercially by industry, and so there are products available for practical, kind of hands-on use and experimentation by students, and also, in their future careers, useful for understanding the architecture. And RISC-V supports a broad range of processors from embedded to high performance, and has offered features, for example, compressed instructions for embedded systems to make that more efficient in hardware. And kind of related to this, it's forward thinking in that it includes, for example, the 128-bit data for future implementations. So it plans on being around for a while with the support of things that we're not necessarily using right now, but will be needed in the future. And like I said before, it offers commercial inexpensive development boards, so students can actually run code on the RISC-V processor. So let's do a bit of a comparison between RISC-V and other architectures. So MIPS is one of the architectures that we've written about before. Very, very much related. So maintains a similar instruction set format. So R-type, I-type, the formats of the instructions are very similar, or at least the categories of them. And the register and instruction naming is follows in parallel, basically, right? Add immediate is add I, load word for reading memory, and the register name saved registers are preceded with the S character, so S0, S1, argument registers A0, etc. But RISC-V gets rid of idiosyncrasies like a branch delay slot, branch offsets relative to PC+4 instead of PC, inconsistent register locations in the instruction encodings, which makes, requires then extra multiplexers to choose, well, which location of the instruction are we going to get that register operand from. And, it happens to have more complex immediate encodings, which, is at a plus or minus. Well, it helps. The reason it does that is to minimize the hardware requirements, but makes it hard for humans to read and, a little bit annoying for encoding. But again, RISC-V is commercially viable, whereas MIPS is, seldom used in current commercial products. Compared to ARM, RISC-V doesn't include conditional execution or complex indexing modes, which complicates the hardware. And it doesn't require the licensing, whereas ARM does. But it does offer 16-bit compressed instructions, just like, or similar to ARM's 16-bit thumb instruction set. So it allows that flexibility for targeting lower power and lower memory devices, such as embedded systems. So the chapters are divided just like the title indicates. Digital design is in the first half of the book in chapters 1 through 5. We start with fundamentals, number systems, binary, choose complement, hexadecimal, logic gates, transistors, power consumption, and then build up to combinational logic. How do we form functions using combinational logic? How do we optimize those functions? And what is the timing of those functions? And then in the third chapter, we talk about sequential logic, building from the state elements, latches, and flip-flops to building finite state machines and parallel systems, both spatial and temporal parallelism, so with pipelining. And we talk about the timing of sequential logic, so how fast can we run this system. And then chapter 4 is really an optional chapter on HDLs, on hardware description languages. We cover both System Verilog and VHDL side by side, so depending on what's needed in the curriculum, can follow either track. But it's optional because the rest of the content of the book doesn't really require it. Of course, we like it because it gives students hands-on experience and very relevant to current digital design practices. But can be skipped if it's not used in a curriculum. And chapter 5, the final chapter of digital design, talks about common digital building blocks like adders, multipliers, dividers, memory systems, logic arrays, and then in the second half of the book, we use those to build the processor. And so really that second half of the book, the computer architecture side, builds on the first half of the book. So in chapter 6, we kind of pop up a level of abstraction to the RISC-V architecture, talk about the instruction set, and also talk about some of the extensions, the floating point and double extensions, and the compressed RVC extension. And we also talk about pseudo instructions and the stack and so forth. And then we dive back into hardware and how the two come together. And so chapter 7 is really kind of the culmination of the book, where we bring the digital design and architecture together to build 3 types of processors: a single cycle processor, multi-cycle, and pipelined RISC-V processor, and talk about performance, execution time. How do we evaluate these processors? And then chapter 8, we talk about memory systems, caches, virtual memory. How do we organize memory systems? And in chapter 9, which is an online chapter, we talk about I/O systems. So memory mapped I/O, serial interfaces, interrupts, motors, other peripherals that you might use. And so we do that in a hands-on approach by using the RED5 breadboard, which has a RISC-V microcontroller on it. And then there are appendices as well, A through C, which talk about, kind of practice of digital systems and implementation in Appendix A. Appendix B is a summary of RISC-V instructions, and Appendix C is on C programming. So we talk about three types of RISC-V processors: single cycle, multi-cycle, and pipeline. And we also talk about, mention advanced microarchitectural techniques such as superscalar, out of order, register renaming in Chapter 7. And in these RISC-V processors, we implement a subset of the RISC-V instruction set: add, subtract, and or set if less than. So these are type instructions, loads and stores, memory accesses, and branches and jumps, as well as some I-type ALU instructions, so immediate ones that can access or use immediate operands. And so here's a picture of the single cycle RISC-V processor, and we developed this, after the, building up with the fundamentals of understanding what these blocks are, instruction memory. The students understand what's underlying that, that picture, register file, ALU. The students have designed these by the time they get to this point. And so we can develop this RISC-V processor, in a matter of, one lecture, even because of the foundation that we've built in the first half of the book. And here's a picture of the multi-cycle RISC-V processor, and finally the pipeline RISC-V processor, which we developed by starting with a single cycle and adding the pipeline registers between them. So we have a set of labs and exercise solutions that accompany the book on the companion website. And the labs require software and hardware. The software is all free, and the hardware is optional, but recommended. We find that students learn a lot more by being able to experiment with it and have hands-on experience. But if cost is an issue, most of the labs can be completed in simulation with the software only. And so we use the Quartus software from Intel, and ModelSim for simulation, Quartus for targeting the field programmable gate array, the FPGA, and then for C code, we use Visual Studio Code, VS Code, and Platform IO. And the board that we use, the FPGA board we use, is the D2-115 board. It costs about $300 for academics, and for the C code for microcontroller labs, we use the Red 5 board, which costs $39.95, about $40. So one thing too is, these can easily be targeted to another FPGA. So for example, if you have Xilinx FPGAs already available, these labs can be retargeted to those other FPGAs that you have available. And so here's a picture of the two hardware pieces: the Red 5 board and the D2-115 board, the FPGA board. So we start with some schematic entry labs. So 1-bit full adder, 7-segment display, and the finite state machine. So we build up to these, and we find that if we started with HDL, with System Verilog, for example, students think of it more as a programming language instead of hardware design. And so we start specifically with schematic entry, so students can be thinking of what hardware do I want to create, right? What kind of hardware am I generating? So when they get to the System Verilog labs, in labs 4 and 5, that mentality of design is already there. And after the first digital design labs, 1 through 5, then we pop up to some C programming labs using the Red 5 board, matrix multiplication, and then a Simon Says game with LEDs and switches. So the students get to build the hardware as well to play that Simon Says game. And then we pop back down into building the processors into microarchitecture, using System Verilog to build the single cycle processor. And then we kind of give them that single cycle processor. It's available in the textbook as well, and all of the HDL for actually all the processors is available for instructors on the companion website. So the single cycle processor we give to them, and then they modify it by extending it to include other instructions, additional instructions, and then they use those building blocks, the register file, the the memories, the ALU that they've built in Lab 5 to then build the multi-cycle data path and control in the last labs, in Labs 9 and 10. And I want to mention too that there are optional labs for assembly programming only. So they write test programs in 8 through 10 to test their processors and load onto their processors using RISC-V assembly. But there are optional assembly labs that can be included after the C programming labs as well. So in conclusion, we've written a textbook and companion material that starts with digital design and builds up to designing several RISC-V processors. And we found that teaching these together, teaching digital design and computer architecture together, enhances student understanding or anyone's understanding of both topics. And so, you know, RISC-V architecture itself is both, you know, easy to understand and commercially relevant. And so that makes it a particularly good architecture for teaching. And teaching the processors from top to bottom, or you know, really bottom to top, from transistors up to the software programming, the software program running on them, really empowers the students. There's no kind of hole in the understanding, right? There's no point where they're like, well, I don't understand that level, but there's a complete understanding of the entire process from top to bottom. So I'd like to acknowledge contributions of our colleague, Josh Brake, professor at Harvey Med College, and numerous reviewers that have given us feedback on our textbook. Thank you.